Welcome to EDU World Space.
This is chapter 21, problem number 52, and this is a very similar problem to example 21-11 of the textbook. However, the main difference between these two problems is that in the example that is solved on the book, you have symmetry in the y direction. We don't have it here. The charge is extending from a y minimum of -4 meters to a y maximum of 2.5 meters here, and x is given to us as 0.25 meters, and the length of the wire is 6.5 meters. The charge that it has is 3.15 microcoulombs. So in part A, we're asked to calculate the EX and X component of the electric field and the Y component of the electric field at point P. Now, one thing that we can use is that the differential form of the electric field is, well, 1/4 pi epsilon naught. If you go back to the example, lambda dy over, well, r squared, in our case, r being square root of x squared plus y squared. What we have in denominator is x squared plus y squared, right? We don't have symmetry this time. What we need to do is we need to calculate the dx as dE times cosine of this angle here, right? That's going to give us dx. Then we can substitute for dE 1/4 pi epsilon naught lambda dy over x squared plus y squared. But let's remember what cosine theta is on a separate note here. Cosine theta is adjacent x over hypotenuse being r, also x over, as you can tell, x squared plus y squared square root of this. So we can substitute for that, for the cosine theta, x squared plus y squared 1/2 that. Now, if we rearrange dEx, then what we have looks something like 1/4 pi epsilon naught lambda x dy over x squared plus y squared 3/2, right? 3/2. Okay, now we're going to take the integral, right? So EX is going to be equal to lambda x over 4 pi epsilon naught. We're taking the integral over y, so I'm pulling out the constants. Now we have x squared plus y squared 3/2. The limits, well, obviously y minimum and y maximum that is given to us in the problem. Now you can see the antiderivatives in the appendix B4 on your textbook. For this one, what we have is that EX is lambda x over 4 pi epsilon naught y over x squared square root of x squared plus y squared is our antiderivative, y minimum, y maximum, right? So let me see. So we have x squared here. One x is going to cancel out the other x, and we can also pull it out. So we can write it as, oh, let's remember what lambda is. Lambda is not directly given to us, but we know how to calculate it. The total charge divided by the length equals the linear charge distribution, so we might as well substitute for that. We have L here, and we have X. Remember this X? So we have that too. And we have y over square root of x squared plus y squared from y minimum to y maximum. All right. So now we can plug in our numbers, right? Q is 3.15 times 10 to the power of -6 coulombs. I converted microcoulombs to coulombs. In denominator, I have 4, 3.14. Epsilon naught is 8.85 times 10 to the power of -12 coulombs square per meter square. and L is 6.5 meters, X is 0.25 meters, and I have Y max was 2.5 meters, right? Divided by 0.25 squared plus 2.5 meters squared minus negative 4 meters divided by square root of 2.25 squared plus negative 4 meter squared. From here, we're going to find the X to be 3.47 times 10 to the power of 4 newtons per coulomb. All right. Now, going to EY. Then DEY, pretty much we're going to follow the same recipe. DE, this time it's going to be sine theta, where, let's remember what sine theta is. Sine theta is going to be opposite over hypotenuse. Y over R, right? Y over R being x squared plus y squared, square root of the summation. DE is 1, well, the negative of it, pardon me, please. The y component is going to be negative because it will be pointing down. So negative 1 over 4 pi epsilon naught. We have lambda dy, right? Over x squared plus y squared. This was our dE with the negative. Now we're going to add the sine y x squared plus y squared, square root of this. Now negative lambda over 4 pi epsilon naught x squared plus y squared to the power of what? 1 plus 1/2. It's going to be 3 over 2. And what else we have? Again, this was lambda, right? Let me write it nicely. And then y dy, right? Let's remember, again, lambda is q over L. So when we're taking the integral, we might as well substitute it there. Negative q over 4 pi epsilon naught L. This is the constant part. We have y dy over x squared plus y squared 3 over 2. Okay. From here, if we take the integral of both sides, ey is going to be equal to negative q over 4 pi epsilon naught L. Integral of y dy over x squared plus y squared 3 over 2. Again, y minimum from y minimum to y maximum. And we can look up this integral again. It's going to be equal to, this part, negative q 4 pi epsilon naught L. It's going to be negative 1 over x squared plus y squared 1/2 from y minimum to y maximum. Now you can see these two negatives are going to cancel each other out. Then what we have is going to be q over 4 pi epsilon naught L and 1 over x squared plus y squared 1/2 from y minimum to y maximum. So we can plug in our numerical values now. So on the new page, Q was 3.15 times 10 to the power of negative 6 coulombs divided by 4 times 3.14 times the epsilon naught, 8.85 times 10 to the power of negative 12 coulomb square Newton meter square. And we have L, right? It's 6.5 meters. And then we have 1 over x squared square root of 0.25 squared plus 2.5 squared minus 1 over, this is a 1 over 0.25 squared plus negative 4 squared. All right. From here, the y component is 647 newtons per coulomb. That's what we're going to find it out to be. Now, this is the answer to part A then. So, as far as part B is concerned, we're asked to determine what the error would be if we use the result of example 11, which is this, lambda over 2 pi epsilon naught x. What will be the error? Express this error as Ex minus E over E. All right, then let's calculate E first, and then we can calculate the error in X, and also we can calculate the error in Y in this form. That's how we're asked. Then E is going to be, lambda is Q over L 2 pi epsilon naught X. Q is 3.15 times 10 to the power of negative 6 coulombs divided by 6.5 times 2 times 3.14 times 8.85 times 10 to the power of negative 12, and X was 0.25. Then from here, the electric field, if we use the answer that we derived from example 21-11, the electric field would be found as 3.48 times 10 to the power of 4 newtons per meter. Now, let's plug in what we have found for E sub x. It was 3.47 times 10 to the power of 4. The minus E that we just calculated, 3.48 times 10 to the power of 4, divided by 3.48 times 10 to the power of 4. What we find here is actually a very, very small error, right? It's going to be equal to negative 0.0034. So this is almost like 0.03%, right? Pardon me, 0.3%. That's pretty small. That's pretty close. Now let's look at the error in the y portion. Ey over E. Ey is 647 divided by 3.48 times 10 to the power of 4. Then what we have here is 0.019. So this corresponds to almost 2%, right? This is almost 2%. Still, it's a very good approximation, right?